All right, everybody, here we are on week 1, day 2, our first online lecture, and that's where we left this slide here. This is where we left with the little baby tugs. And now we're all ready for class, and I've got my stuff. I just wiped down since I was using this computer at school. Now it's on my kitchen counter. I wiped that down. That's good. You know, we got the teacher's okay. So there's the teacher's apple. We got a little model of a ship that we're going to use here. I got my colored pencils and pens. We got that stuff, and we got the book. So let's start right off with a little bit of random attendance. So this is what I'm going to ask you to do. If I call your name, I want you to send me a text. I want you to send me a text with a thumbs up and said something along the lines of just a few words. I was there, I heard you, I'm responding to week 1, day 2. And so let's do Dan Garand and Evan McIntyre and Sydney Underhill. And let's see, we'll also do Ethan Corbett. We'll do Brian Graff. We'll do Christian Shepard. And how about David Estes? And then let's do Mont Blair. Let's do Olivia Mitchell. And how about Caden Pond? And also Joe Van Ness. And why don't you guys, all of you, you people, why don't you give me that thing so I will do that random check every time so I'll know that you're here. So you see that we're looking down. I've got sort of this document cam stuff, and then we'll go to the PowerPoints. Very good. So the first thing we're going to talk about is how does pivot point, that's where we left up on Monday's class, how does pivot point, how does it affect when we start coming into that tugboat, and we've got tugs, ship, and we got this 3 vessels now, 2 tugs and 1 ship. What happens when these tugs, now here's the deal, that these equal power tugs are pushing at points equal distance from the midpoint, the mid-body, and that happens to be where the pivot point, the center of gravity, so that this distance here, from here to there, and this distance from the blue dot, the pivot point, over to here, it's the same distance. Let's say this is a 600-foot ship, and it's 250 feet from the pivot point, the center of gravity, over to the after tug, and also 250 feet to the forward tug. How strong are the tugboats? Let's say they're 1,000 horsepower, and they're pushing with half their horsepower. And so if they do that, what's going to happen? Well, each tug is just going to generate some type of motion on the ship with this combined tugs, and we have to discover what that is. And because the ship is making no headway or sternway, it's dead in the water, the pivot point is right there in the middle. If that same vessel now, in this diagram down here, if it starts to make headway of 2 or 3 or 4 knots, let's just say that, and there's the headway, the pivot point will now move to this location. The tugs haven't changed. They're still pushing with 500 horsepower. They're still pushing at the same location. The distance that they are applying the force is different. This is like the unbalanced seesaw at the playground that we talked about on Monday's class. And there's a much longer lever here. And when we're going astern, the opposite happens. The pivot point moves aft when you're going astern. Now the after tug has a different lever, length of the lever, it's shorter, and the forward tug has a longer lever. So that's what's important. It's about where the pivot point is, the placement of the tug. We're not changing the horsepower or the amount of throttle on the tugs in these 3 examples. No headway, no sternway, dead in the water, making headway, and making sternway. We're going to see, I'm trying to indicate this with the diagram, and I'm going to show you on my tabletop station here. I'll show you that in just a minute. Well, here comes a tug. It's going to be coming into the harbor, and this piece of white paper represents the dock that it's going to go to. So this ship is coming in here, and the first tug arrives and stands by, and the ship comes along, and the second tug comes alongside like this and starts to get in position. And now we're going to get to this location here. The tugs are going to work up and get into position on the vessel, and the ship is stopped. In other words, the pivot point is there in the middle. Both tugs start pushing with equal power. Like I said, maybe 500 horsepower or half throttle. They're going to do about half. Because the pivot point is in the middle, there's no wind and current. This vessel is going to move laterally, sideways, towards the dock. Now, there might be a little bit of play there, but it could be, and the tugs can control that, and would be brought right into position. That's the way it would work. All right, the pivot point was in the middle. Each vessel, each tugboat, had the same amount of distance from the pivot point to, at the tip of the red pen. This distance here from the red to the green is the same as this distance here from the red to the green. Each lever is going to allow each tug, using the same amount of force, is going to do the same amount of work. So they get pure sideways, or I like to use the word lateral motion. So let's we're going to back this up. Now, if this ship were to be moving ahead, let's take the tugboats out of the way for a minute, we'll just put them off. If that ship was moving ahead, we would know that the pivot point would move forward. If it was moving ahead like this, the pivot point would be up here where my red pen is. Now, if we were to engage the tugs, what would happen? If we started to move, again, as I said, we're moving ahead, so the pivot point is going to move to the forward portion of the vessel. Think of that pivot point as right there. The tugs are pushing with equal power. They're in there. So yeah, if we could separate these components, the tug wants to do this, the ship wants to do this, the tugboats want to do this, but the resultant motion would be that it would be more of a twisting motion with the ship, because that forward tug couldn't deliver the same amount of work because of its distance from the fulcrum, from the pivot point. So we would end up with a sort of sliding through the water, but a twisting effect like this. Both tugs are pushing with 500 horsepower. The ship is trying to go straight. It's not using its rudder, but that would be the net effect. Now let's go back up and let's say that let's start and we'll go astern, and we'll put the pivot point now back here because the vessel is moving astern. Tugs are in the same spot. What's going to happen? Yeah, the ship wants to go astern. Separate from that, the tugs want to push it sideways, but if you combine that, what happens is it wants to pivot around like this. There was no wind or current doing that. There was no use of the rudder by the tug, but just because of the location, and you think back to that fulcrum of the seesaw or that board that had the rocks piled up on it that I showed you in class on the first day, you think about where that pivot point is and how it affects the motion of the ship. It's kind of interesting. And we really need to work on that. That's going to be that, on exam number 1, that's going to be that part 2 of exam number 1 that you're going to do at home. And I'm going to look for a real thorough and well-written explanation of that. Well, it's not only always the tugboats which are being pushing the side of the ship. It might just be the wind which is pushing the ship, and we have to deal with wind all the time. So here's the ship again, and we see this. We got this little model of a ship here, and I'll lay it over there so you can see it. And we've got the wind blowing out of the west. Wind is from, current is towards, so this is a westerly wind blowing out of the west here, and it's enough so that you could feel the ship. You could feel it on the ship. You'd have a noticeable effect, particularly with all these containers stacked up on deck. It would have a whole lot of surface area to work on. So here's the same diagram, but now the tugs are gone and we've got the ship making no headway, the ship moving ahead and the ship moving astern. We've got the wind blowing on the side of the vessel. Now I'm going to ask you a question. I want you to respond in the YouTube in the comments. This is for everybody in the class. This is how I'll sort of know, and it'll be an indication of your participation in the class. What is that wind speed? Now you see these wind arrows. I think most of you should know this as juniors. Let's see, we've got a long feather and a short feather, and you should be saying, well, that's this much wind speed. And this much wind speed, let's see, long feathers are 10 and short feathers are always 5. So this is a 15-knot wind. Got a 15-knot wind blowing from the north in this case, and it's blowing on the side of the ship. And we'll go back to our tabletop display and we'll look and we'll explore what happens when we're dead in the water, what happens when we're moving ahead with a forward pivot point, what happens when we're moving astern with the after pivot point. So now we've got this 15 knot wind here. It's a short and a long feather. That was 15 knots. The pivot point is right there in the middle. And we're blowing on the side of the ship. The pivot point is in the middle of the ship, right at the center of gravity. And so as this wind blew, we would have just pure lateral motion. Just like with the tugs, applying that force, we would have pure sideways or lateral motion. All right, well, what happens if we now, we have the wind blowing the same way, but the ship is moving ahead. The ship's now moving ahead, coming across here like this. The pivot point now moves to this forward part of the vessel. And so what's going to happen is, let's talk about the wind first. The wind wants to do this. All right, we get some lateral motion, but because of the pivot point moving forward, the wind, everything after the pivot point is behind the pivot point. We have this long amount of surface area compared to a short amount of surface area, so we get some rotational motion. That's what the wind wants to do. The ship wants to go straight. The wind wants to do this. It also wants to set it down. So now we've got longitudinal, we've got sideways, and we've got rotational. The net result would be something like this. Oh, now when the vessel, let's see, we talked about when the vessel is stopped, the pivot point's in the middle. We talked about when the vessel is moving ahead, the pivot point's forward. And what about when we are going astern? So the pivot point moves aft. Well, the wind effect, let's see. The wind wants to push it sideways, but it also wants to have a rotational, because of the short surface amount of surface area here, longer here. Let me show you on, I'll show you my fingers like this, a longer area from this finger to this finger, as opposed from this finger to this finger. So that wants to introduce some rotational motion. And so here is the wind now blowing the vessel. We've talked about going ahead with the pivot point forward. We talked about having the pivot point in the middle. Now we're going astern, and so with the winds blowing, it's only operating on this much as opposed to this much of the vessel. The short amount after the pivot point, this long amount of steel side of the ship, forward of the pivot point. Now the ship wants to have some longitudinal forward motion, or in this case, this after motion. In this case, this after motion. The wind wants to blow it sideways, but there's a rotational aspect of it, and it wants to blow it this way as well. There needs to be, we put that all together, and it's going to be going astern, it's going to be rotating, it's going to be blowing down to the south, it's going to be this type of motion here. And so that is it's a little bit difficult to show. I hope you study that. I hope you think about that. It's all about the pivot point, the motion of the force, the wind of the tugboats. We made that comparison, and where the pivot point is, and whether or not the ship is going astern, whether or not it's stopped, or if it's going ahead. So we can talk about more. You can ask me any questions on that. So I'll just come on camera a little bit, and so that I am here, and we're going to talk about transverse thrust next. And so the transverse thrust is going to be the sideways force, the side force of the propeller. Well, first of all, we need to know that all vessels are either single screw vessels, single propeller vessels, are either right-handed or left-hand turning vessels. And so 95, 98, I don't know, some really large percentage, and you could find pockets of the world where it's not that percentage. But basically, let's say 98% of the single screw vessels in the world are going to be right-hand turning. In other words, they are right-handed props. They turn clockwise. When you are viewing them from astern, and I think most of you know this, they turn counterclockwise. They return in the reverse direction. They turn this way, and I'll make my pointer go that way when you're going astern. Let's go a little bit further. This thing, transverse thrust, is a resultant of that turning force, which happens of the propeller. Now, sometimes this is known as paddle wheel effect. Sometimes it's known as walking to port or backing to port. Sometimes it's known as side effect. In any event, it all means the same thing. A single screw, right-handed propeller, will cause a vessel to back to port when it's going astern. It's transverse thrust. Here's the paddle wheel effect. Now, oddly, we've taken a paddle wheel, like from an old, Mississippi riverboat, and we've stuck it on the back of a traditional single propeller, single screw ship, and now we've got a paddle wheel. It wouldn't have no longitudinal driving ahead force. It would all be transverse force, pulling the vessel to sideways. And that's, for some people, that's a nice way to think about it. And here's just another diagram. It's viewed from astern. Vessel is going astern. The propeller is turning counterclockwise. It's a right-handed propeller going ahead, but now it's going counterclockwise, and it is pulling the stern to port. Vessel turning the stern revolutions. All right, perfect. One last view of something that is transverse thrust. This is maybe the conning position of the ship. It's not the pivot point. The vessel's going astern, and the transverse thrust drags the stern off in this direction, walking to port. Now, I know many of you have learned that in the past, and so we'll be real quick on that. Let's talk about something new. We're going to talk about the rudder and the propeller. We're going to talk about some docking scenarios, and then back and fill maneuvers. And you might have different names for those, that back and fill, but we'll talk about it. First of all, the rudder and the propeller. So the key element is to consider or think about is that water has to be flowing by the rudder surface in order for the rudder to produce any turning effect. And clearly, last time I checked, the rudder is hanging, or it's placed here aft of the propeller disc. And here's two different views, a stern view and a side view. So as the water squirts out the prop wash, it's going to impinge, it's going to strike the rudder. Water molecules need to strike the rudder surface when turning ahead revolutions. If you're going astern, the prop wash is running up under the vessel. That's different. But when you're going ahead, the prop wash is coming out astern. Well, it's interesting that a rudder is kind of like, well, it's a hydrofoil. It happens to be on a vertical axis. Now, when we talk, we could do an airfoil or an airplane wing, in other words. We could do a comparison, but an airplane wing, an airfoil, in this case, it would be on a horizontal plane. And so here's the airplane wing with a side view, and we see the airflow, not the water flow, but the airflow, and it creates a high and low pressure. The low pressure is on top of the wing, the high pressure is on the bottom. There's a difference, and that creates a lift in the terminology of an aircraft and flying. And if you get too much of an angle there, we actually end up with some cavitation. That's usually a word we associate with propellers and rudders in the water, but you could have that turbulence, that cavitation behind an aircraft wing, that air turbulence. So now we switch over to the rudder surface, and we can imagine that airfoil, notice the shape of the rudder, it's not just a plank, but on most vessels of size, it's going to have a little bit more of a hydrodynamic shape to it. It's going to be configured. It's equal on both sides, unlike an aircraft wing. An aircraft wing is designed to lift one way. A rudder has to, of course, go left and right. Developing lift, I would put that word in air quotes if you could see me on the screen here, and it would be a lift either to port or to starboard, not like up, not lift in the sense of an aircraft wing, which is going upwards. All right, so there's a simple concept to remember that I might ask you about on an exam. So how do we get that motion by the rudder surface of those water molecules? Well, first of all, we've talked about the propeller prop wash coming back and striking the rudder. You could also have the motion of the vessel. Propeller could be stopped, but you've either got headway or sternway. It's residual motion of the vessel. You've stopped the propeller. You're still drifting ahead. You're going to have water going by the rudder. And you could be at the dock tied up. You're not going anywhere. You're 0 speed over the ground, but the current is flowing underneath the vessel. Perfect example would be any of our Academy vessels, in particular the State of Maine, tied up at the dock on the Bagaduce River, stemming the current on an ebb flow. There, if you use the rudder, we energize that steering gear room, and you got the rudder, we could steer that ship right alongside the dock. We wouldn't have any headway or sternway, but we'd have no rudder. The rudder would be being used, but not the propeller. It's pretty interesting stuff. It's more likely than not that you would have 2 or 3 of those things happening at once. So your brain of a ship handler needs to be considering all of those things. Another thought that I want to put onto you is thinking about the rudder and the propeller. A method that the instructors in the lab are going to talk about, and we've already discussed this between them and I, and this is an important thing in each of our thought processes for your instructors, to position the rudder first and then to give a kick ahead. Maneuvering a ship at a tight spot, you've got to have to be careful. You have to be judicious in the use of your rudder and your propeller. But in this case, it's probably a good idea or a good concept to practice. Position the rudder first, hard left, hard right, whatever it was, left 20, left port 20 or starboard 20, whatever that might be, and then to give it that short pulse of ahead energy. And the instructors will talk about that in the labs. Now there's docking situations. We'll talk a little bit about what you're doing in lab. I know what you're doing in lab. You're out there working on the buoy, you're practicing going ahead, making turns, doing figure eights. You're going to be coming alongside the dock soon. You'll be coming along the town dock. And because these are right-handed propellers, it's probably the most desirable situation is to bring your vessel into the dock port side too. And that's because of transverse thrust, because it will pull, or it will, some people will say it sucks the stern in towards the float. Well, it doesn't really suck the stern into the float. It transverse thrust pulls the stern in towards the float. This area of the ship is the vessel, and this could be a 32-foot MMA 1 or 2, or it could be the Deborah Ellen or Lumpy. Any of those vessels are going to behave the same way. I would make a little bit of I would tend to say this about when you're making that approach angle, you're port side 2, you have a right-handed propeller. When you're about 3 or 4 ship lengths off the dock, here's a phrase for you: scan and plan. I've already told you about go slow, think ahead, be patient, let the boat do what it needs to do, go slow, think ahead what's happening, but also put your eyeballs on that float, make sure there's nothing there which is going to damage the ship, make sure there's nothing in the water, make sure that you're clear to come along the dock area, in this case the town floats maybe, and I call that scan and plan. Well, anyway, you're going to be about 3 to 4 boat lengths, 2 to 3 at the very minimum off the dock, and yet at that point you almost have bare steerage way. You might even be stopped engines, just creeping ahead. You'll want to go really, really slow. If you're coming along starboard side too, then certainly you're going to want to decrease that approach angle. I mean, let's look at that again. We'll go back here. Port side 2, really steep, almost a 40-45 degree angle to the dock. Right here, if we drew this angle from here down to the dock and then along the face of the dock, that's about a 45 degree angle. And if we're coming in starboard side 2, because of transverse thrust, it's going to pull the stern away. And the instructors will talk about that. You're going to have and it gets even more complicated when you've got an astern current, and that's what's going to make this a challenge. The next little detail I'm going to talk about is when you're doing this maneuver called a back and fill maneuver. That won't be for probably 3 or 4 weeks before you're doing that, where you have to enter a small, confined area, a small boat basin, like at Maine Maritime, and turn your vessel in that area where the size of the area nearly equals your boat length. So let's look at what that might look like in a couple of different steps. And so here's position number 1, 2, and 3. You can imagine the finger piers for the boat lift are coming out over here. Maybe the tug pin will go, it is tied up here. The Bowden is parked in here, other vessels and launches, and you have to come into position number 1, 2, and 3. The key to this, and this is because you are a right-handed propeller, you need to initiate that back and fill maneuver by coming to starboard. And then positions number 4 and 5, well, they're going to look like this. And then 4 and 5 are using transverse thrust to pull the stern. This model is Deborah Ellen, and double-endered, the 26-foot Deborah Ellen. And it could be lumpy. It's going to be the same type of thing, or any of these boats. You're going to back this off to port, just tuck that stern pretty close into the corner here, watching out for other craft, and then you're going to come to the next position, 6, and then you're going to be going ahead and coming out in this direction. If we look at that all together, it looks something like that. Let's go back to the tabletop and let's see what we got there. So now we have the same ship. It's a big ship. It's a container ship. It's 400, 500, 600, 700 feet long, and we have to come into this very tight basin, and we have to do a back and fill maneuver. Well, first of all, knowing that I'm going to have a right-hand turning propeller, I'm going to initiate that turn to starboard, and I'm going to come over, and I'm going to get as close as I feel comfortable with. Because it's a right-handed single screw propeller, I'm going to back it down to port, and I'm going to tuck this in over here. Then I'm going to come ahead with some, with some right rudder, some starboard rudder, and I'm going to come out in this direction. Again, that motion looks like this, and then that's 1, and then there's 2, and then there's 3. But perhaps you're saying to yourself, well, I think I'd like to try that differently. I'm a little bit contrary today, and I want to come over and I want to go to the left first. I understand it's a right-handed propeller. It's going to back to port, but I don't care. I want to do it this way. So let's see what happens. We're going to come over here. We're going to go left. That worked out pretty good. We didn't hit the dock. We got pretty close. Then we start backing it. Well, what's going to happen? As I back, it's going to pull the stern over to port. Well, that's not really good. So you come ahead again, then you back, and you mess around with the rudder, but that's not going to have any effect. So you keep doing it. That's the definition of crazy. You've heard that definition. Keep doing the same thing, but over and over again, but expecting a different result. You're doing the same thing. And you'll see young ship drivers, inexperienced people doing that maneuver. Because it's right-handed propeller, you need to come to starboard initially. Then you back it around to port, and then you come out. So you're going to practice that maneuver. It becomes particularly tricky down there in the boat basin because the current is either flowing this way along the harbor, or, because here's the dock going out to the ship, here's the floats in the MMA parking lot, and here is the, the dock where the other small boats are also tied up in the Pentago. It's down here. And so you visualize this boat basin with either an ebb current or a flood current, tidal currents, which make that particularly difficult. It's challenging. And it is challenging to do those maneuvers, as you suspect and as you know. As we get here towards the end of this week 1, day 2 lecture, boy, we're going to talk about rate of turn and a rate of turn indicator. This would be a piece of equipment up there in the wheelhouse, the bridge of the ship, and it's a readout that some of you are familiar with. Not everybody has seen this. It's a rate of turn. ROT is the abbreviation. It's mounted in the wheelhouse. It tracks, it calculates, it keeps track of, and it shows graphically with usually an analog display, and it'll show, we'll come down here, starboard turn or port turn. Now this is not rudder angle. This is reading out it's getting information from the gyro, how fast, how much of a course change you're having, and it comes out, it reads out in degrees per minute. If you had a rate of turn on a ship, on a vessel, of 10 degrees per minute, that would be an indication that it would take 36 minutes. 10 times 36 is 360 degrees. It would be 36 minutes to make a big full circle. It would be, if you had a rate of turn of 20, it would be 18 minutes. And some of the VOTs, the students would be thinking, that's not even possible. Vessels that I work on, that I'm familiar with, they turn much quicker than that. But I tell you that the large ships, a rate of turn or 10 or even 20 degrees is a pretty high rate of turn when you're maneuvering a large vessel. The next topic is something called directional stability. It's either positive, negative, or neutral. And look at what it says here. Positive is a vessel tends to steady up once the rudder has been placed amidship. You're making a turn, you put the rudder amidships, and the vessel tends to steady up very, very nicely and go in a straight course. That's a good thing. Negative directional stability is when, let's see, we go, vessel swings at an increasing rate of turn once the rudder has been placed amidships. Well, that's a pretty bad vessel. Vessel swings at an increasing rate of turn once you have put the rudder back to the middle. It's very dangerous and very difficult to steer that ship. And neutral directional stability, vessel swings at a constant rate of turn once the rudder has been placed amidships. Well, that's not very good either, but that's called neutral directional stability. There is a different way of thinking about this. You could think about this in this fashion. You could say that vessels are either directionally stable or they are unstable. And I could take that one step further and say they're a good vessel, a good ship. They steer nicely, they steer easily, they hold their course well, or not so much. They're unstable. There's a little italicized blurb there that you can read. Accordingly, it may be stated that moored rudder applied for a longer period of time is required to check the swing of a directionally unstable ship than is required to start that swing. A little bit of rudder gets it swinging, and you have to use all your rudder the other way to stop that swing. Not a very good thing if you're operating as a pilot, as many alumni are in the Houston Ship Channel. Next thing I want to talk about is vessel motions in a seaway, motions of a vessel in a seaway. Now we know that we have an Y, a Z, and an X axis, and we can think about it in that term. But the terms we use in this business, we talk about heave, pitch, roll, sway, yaw, and surge, all the way down here. Heave, pitch, roll, sway, yaw, surge. You should be able to connect any of those to these arrows. You should be able to write those down. You should be able to recite them and know which ones they are. Which one is roll, which one is pitch, let's see, I started with roll. Which one is heave? Let's see, there's heave, here is pitch, here is roll, here is sway. Let's see, there's sway right there. Oh, that's yaw, I'm sorry. And here we have surge, which is this one right here. There's sway. So you should be able to connect those and know what those are. I'll be asking you that simple question: heave, pitch, roll, sway, yaw, surge on exam number 1. But when we're ship handling, we're not out to sea, we're not in the seaway, we are in the harbor, we're not probably rolling, we're not surging, we're not pitching, we are pretty much level. So we use the words for ship handling, we use the words longitudinal motion, that's fore and aft motion here. We use the word lateral motion, that's side motion. And then we use the word rotational motion, so longitudinal, lateral, and rotational motion. When I ask you on the exam, I say give me the 3 motions as discussed in the PowerPoint in the lecture for ship handling: longitudinal, lateral, rotational. Not the other ones, that's out in the seaway. I'll ask you about those too, but I'll particularly, and don't say, front and back motion, sideways motion, and twisty-wisty motion. No, not happening. It's longitudinal. You got to use the right words at the right time. Longitudinal, lateral, and rotational motion. Here's a rule of thumb that you also need to know. And this rule of thumb is 100 feet in 1 minute equals 1 knot. Yeah, there's some decimal points there, but as a rule of thumb, that works pretty good. If your ship's doing 1 knot, you're going to travel 100 feet in 1 minute. If you're doing 2 knots, well, let's see, you're going to travel 200 feet in 1 minute. Roger that? So you have that in your brain. Remember that, 1 knot, 1 minute, 100 feet. Yeah, there's logs, there's electronics, and they show us various ways of displaying our information. That's all good stuff, but that doesn't preclude you knowing that 100 feet, 1 minute, 1 knot rule. Sure, GPS works great, but understand that GPS is always, and I know it's accurate, and I know it's good, most, if not all, but there's that little if there, but it is still historical information. It is what you were doing. It's what your speed was. And it's not the way people dock a ship by staring at the GPS or staring at the GPS and the little ship drawing on the ECDIS. That's not the way we do it. We're getting to the end here, and I want to give you another one. So this is 100 horsepower equals 1 ton of bollard pull. Now I will absolutely ask you that question on exam number 1. I'm going to say, how many horsepower equals 1 ton of bollard pull, or some function of that? I'm going to say 1 ton of bollard pull is how many horsepower? You get it. Well, it's true. So if you have a 1,000 horsepower tugboat, that tugboat, and that's a term which is used often in workboats and tugboats, it's 1,000 horsepower on a tugboat is 10 tons of bollard pull. You just do the math. You might have 2,000 horsepower, then you'd have 20 tons. If you've got 5,000 horsepower on a tugboat, you've got 50 tons of bollard pull. How do you actually measure that? Well, it can be measured using this diagram here. You see this is called a force gauge. And so let's go on to the next slide, and we'll get a picture here. You'll see some crew out rigging it up, and there's some shackles and things happening. I'll back this picture out a little bit more, and you can see this tugboat. Now this is a Z-drive tugboat. I'll explain later on in the class how we know that. And it's starting to pull on that line. You can start to make it out, but let's go to even a better picture here. And you can just imagine the amount of turbulence and the amount that's, they're coming full ahead on the engines. I would have moved that vessel, that car, or maybe it's a company car, so maybe somebody doesn't care. Also note there's a little safety line between two bollards. If this one starts to let go, that's going to keep this piece of the bollard, or these shackles, of springing back to the ship. Very interesting, and that is a stress meter or pull meter. It's a gauge, and I'll go back to the very first slide for a minute. So we see a force gauge on there. Notice the little antenna that's going to be reading out to a remote location. And I got one more slide for you. You might have asked, how much is transverse thrust? What is the amount of, how strong is transverse thrust? Well, it is 5 to 10% of the applied astern power. So let's say you're going half astern. So it's about 5 or 10% of that half astern is devoted towards side thrust. And let's maybe use the word bollard force in there. If you've got 5 tons of force going astern, it's going to be about half a ton, maybe a quarter of a ton to a half a ton of thrust off to the side. So just remember that. Transverse thrust is 5 to 10% of the applied stern power, if that question ever comes up. Hint, hint. Okay, so I think we're all done. We've finished up. I know we finished up. And we finished up on the lecture for week 1, day 2, and that's the online version. And I've asked you some questions. I asked you about what the indication of the wind vectors, the long feather and the short feather. And remember that if I called your name at the beginning, send me by text. You're going to respond to the wind question. You're going to respond on the YouTube comments. Give me a thumbs up, just, everybody, so we can see lots of feedback there. And also give me, if I gave you the roll call, you're going to respond to, thumbs up, Captain Teal. I watched the class, but you could do that one by text. I don't want to make it too complicated, but I also want to make it easy for me. So all set, thumbs up, roger that, and I'll see you in class on Monday. Take care.